Hi guys, today I'm going to go through the worked examples from exercise 5.4. So that's applications of exponential functions. So there's only one example here, so I might actually do a few of the actual questions as well, just so you can get more of an idea how to go about these. So let's start with worked example 8. So the number of bacterial cells on a culture plate N can be defined by this rule here. So I'll just highlight that because that is going to be very important. Where T is the time in seconds, so just be careful that you are really, careful with the units there, whether it's seconds or minutes or hours or whatever. The culture has been multiplying. Okay, so how many bacterial cells are initially present? So initially is a key word, and of course that would mean when the time is 0. So we would say N of 0 equals 2000 e to the 0.3 t, and t is 0. And of course, well, this is going to equal e to the power of 0. Anything to the power of 0 is 1. So it means n of 0 equals 2000. So we have 2000 cells initially present. Okay. How many bacterial cells to the nearest whole number are present after 10 seconds? So that's pretty easy. We're just subbing in a 10. N of 10 is going to be 2000 e to the 0.3 times 10. So that's 2000 e to the power of 3. And well, if we were to put that into CAS and put it to the nearest whole number, we're going to get 40,171 bacterial cells. Okay, so simply subbing in the values there, that's pretty easy. Okay, at what rate is the bacterial population multiplying after 10 seconds? So rate, when you see that, that's a key word, at what rate, and it's going to refer to our derivative. So we're going to need to derive the function, and it's saying essentially what is n dash of 10. So after 10 seconds, what's the rate of multiplication of bacterial cells? So we're going to need n dash of 10. So first of all, we'll need n dash. So n of t is 2000 e to the 0.3 t, and well, n dash of t, well, remember we take the 0.3 and multiply it by 2000. 2000 times 0.3, we get 600 e to the 0.3 t. So that's our derivative function. And then, well, now we want to know after 10 seconds the rate. So we use the rate equation and we sub a 10 for t. And we're going to get 12,051. So our units for that, or how we could interpret that would be the population is growing at a rate of 12,051 bacteria per second at t equals 10 seconds. Okay, so that completes the worked example. So I'm going to now do, I think the first 4 I'll do. 1, 2, 3, maybe the first 3. All right, so let's see. These ones, the first 2 are a little bit different. So this is tech-free, and we're given a graph here, and that graph is the function f, which is given to us here, where q is a constant. So first of all, we're being asked to find the value of q. So if we're trying to find the value of q, then, well, we should sub in a point to do that. And the point where we have both the x and y value is 0, 0. So we can say 0 equals e to the 2 times 0 plus q e to the 0 plus 3. And be careful because, of course, anything to the power of 0 is 1, not 0. 0 equals e to the power of 2 times 0, so e to the power of 0 is 1, plus q, e to the power of 0, so it's 1q, plus 3. So 0 equals 4 plus q, and that means q is going to equal -4. So I found the value of q, and look, I'm going to write the equation out again, just so that we have it there. E to the 2x minus 4e to the x plus 3. Okay, so now it asks us to find the exact value of m, where m is a constant and m0 are the coordinates of the point where the function intersects the x-axis. So we can see there's two x-intercepts, one when x is 0 and one when it's m. So let's say x-intercept is when y equals 0. So that means e to the 2x minus 4e to the x plus 3 equals 0. And by now you should be getting quite good, or you want to be getting quite good at noticing the quadratic factorization. And we can say, let z equal e to the x. Therefore, z squared minus 4z plus 3 equals 0. And of course then, well, z times z is z squared, and -3 times -1 is positive 3. -1z minus 3z equals -4z. Yes, that's the middle term. So we have z minus 3, z minus 1 equals 0. Okay, so z minus 3 can equal 0, so z could equal 3, and z minus 1 can equal 0, so z equals 1. And of course z is e to the x. So in this case, x equals log e1, and well, anything to the power of 0 equals 1, so x equals 0. And then this one, well, x equals log e3. So we've got two answers, two x-intercepts, and let's not forget what the question is actually asking us. It's asking us to find the value of m, and m is one of the x-intercepts. So we've done all that work, we've found both x-intercepts. One is where x equals 0, there it is there. The other one, well, is our m value of log e3. So x equals log e3. So in that case, the value of m must be log e3. So therefore, m equals log e3. So that would actually be our answer there, because we're being asked to find the value of m. I don't think we're asked to state it in coordinates. Yep, so find the exact value of m. Okay, find the derivative function of f dash of x. Okay, so let's scroll over here. So f of x is e to the 2x minus 4e to the x plus 3, and f dash of x, well, 2e to the 2x minus 4e to the x, and then of course the 3 will go, because that's just x to the power of 0 there. So we'll eliminate that. So that was pretty easy. There's our f dash of x. And lastly, so I've done those, find the gradient of the curve where it intersects the y-axis. So where does it intersect the y-axis? It intersects when x equals 0, at 0, 0. So find the gradient at x equals 0. And I mean, it's the point 0, 0, but of course when we're finding the gradient, we've got a gradient function. We need to sub in the x value of the point, not the y value. The y value does not have any relevance to finding the gradient. The y value is from the y graph. The gradient is given by the gradient function. So the gradient at 0, 0 is going to be f dash of 0 equals 2e to the 2 times 0 minus 4e to the 0, which is 2e to the power of 0 is 1 minus 4 times 1 is minus 4, so it's -2. So f dash of 0 is -2. So the gradient at the point where the curve intersects the y-axis, or at x equals 0, is -2. All right, so that's question 1. let's do question 2. I think is reasonably similar. Let's have a look. So the graph shown is out of the function f of x, where z is a constant. Okay, find the value of z. So it's the same deal, finding the value of z. So f of x equals e to the negative 2x plus z e to the negative x plus 2. And, well, I'm going to sub in the point that we know, so 0, 0. So 0 equals e to the negative 2 times 0 plus 2e to the negative 0 plus 2. 0 equals, well, this is 1 plus 2 times 1 is 2. Oh, that's a z, sorry. Better write it properly. Plus 2. So z equals negative 3. So that's our first part. And this means that we've got the whole function now without any random variables there. So I'm just going to write that there. F of x equals e to the negative 2x plus, minus 3 minus 3e to the negative x plus 2. So this is our function now, and now we're looking for the value of n, where n is, well, the x-coordinate of the x-intercept, the other x-intercept. So x-intercept is when y equals 0, and that's e to the negative 2x minus 3e to the negative x plus 2 equals 0. Now, this is quite a good one, and I wanted to do this even though this question is quite similar to question 1, because this has a negative power here. So, I mean, you know, there's different ways that you could go about this. I'm going to say let z equal e to the negative x. So that means, well, again, for the same reason, e to the negative x squared minus 3e to the negative x plus 2 equals 0, and then we're subbing z, so z squared minus 3z plus 2 equals 0. So in the previous example we had a positive power x, so z was e to the x. Now it's e to the negative x. So let's cross multiply again. Neg 2 times neg 1, neg 1z minus 2z equals neg 3z. And you don't necessarily have to do the check. I find it handy just in case you make a silly mistake. You can really easily pick it up by doing the cross multiplication method. So we have z minus 2, z minus 1 equals 0, z equals 2, and z equals 1. So e to the neg x equals 2, and e to the neg x equals 1, and, well, neg x equals log e2, and neg x equals log e1. Well, x equals negative log e2, and x equals, well, log e1 is 0, so negative 0 is still 0. So that one's complete. This one you might like to write it as x equals log e half. And the reason that's log e half is 2 to the power of negative 1 is going to be half. So our two x-intercepts occur when x is 0 and x is log e half. So that must mean that our value of n is log e half because the other one is 0. So my final answer there, remembering we want to actually answer the question, n, therefore n equals log e half. So that's our answer that we're looking for. Okay, find the derivative function of f dash of x, or f dash of x, so that's pretty straightforward. Equals, all right, so negative 2 times e, negative 2e to the negative 2x, negative 1 times negative 3 is positive 3, e to the negative x, and then the 2 will go. So that's our derivative function. And finally, find the gradient of the curve where it passes through the origin. So, well, again, we're just subbing in a 0, so it's f dash of 0 is going to be neg 2e to the neg 2 times 0 plus 3e to the neg 0, which is negative 2 times 1, which is negative 2, plus 3 times 1 is 3, so it equals 1. So the gradient at the origin is 1. And that is the end, of question 2. So quite similar, question 1 and 2. I think just the difference being that with the negative substitution for z, whereas question 1 had a positive. Let's do one more, and this one looks like it is a little bit different, more similar to the first, to the worked example, which we did first. So the mass in grams of a radioactive substance is initially 20 grams. 30 years later, its mass is 19.4 grams. If the mass in any year is given by that, then we do what we need to do. So initially, it says the mass is 20 grams. So when T equals 0, i.e. initially, M equals 20. And when T equals 30, so 30 years later, M equals 19.4. So I think it's good to just write that there, and you could even make it into 2 points. So they're ready to be used in the question. No doubt we'll need it. Where T is the time in years, and actually I probably should have read that first, and M0 is the constant. Okay, so find the value of M0. So I'm going to sub in one of the points, and actually I'm just going to sub in that point. So 20 equals M0 e to the neg 0.00152 T. So obviously this is going to be 0, so this whole thing is 1. So that means M0 equals 20. And of course, using the one where T equals 0 is very much better than using 30 and 19.4. So that's our first bit. So now we have our equation being M equals 20 e to the power of negative 0.00152 t. And really this value here, the M0, A0, it's often called, is the original amount, the amount that you start with. So really, I mean, you could have really written that in straight away. The annual rate of decay. Okay, so the annual rate of decay at the rate at which it's decaying. So let's do that. So M, I'll write it again up here, equals 20 e to the neg 0.00152 t. And then the annual rate of decay, rate is our key word, telling us it's the derivative. And then I'm just going to be multiplying negative 0.00152 times 20 e to the, well, this thing again, it's just a little bit annoying to write, 0.00152t. So this is our derivative function, and this here, I did it before on CAS, and it's negative 0.0304 e to the negative 0.00152t. So our annual rate of decay, so the change in mass over time in years, so rate of decay is given by that. So that's part B. And the rate of decay after 30 years, well, that really makes sense that we're just subbing a 30 into the value of t here. So part C, we're going to have, well, dm over d30 is going to be negative 0.0304 e to the power of negative 0.00152 and 30. And as I found earlier, that is going to be negative 0.0291. So it's decaying at a rate of 0.0291 grams per year. I probably should write that on. So that would be our final answer there. And look, you can say negative or you can say decaying at that rate. You wouldn't say decaying at negative. That's a double negative there. So that completes the worked example and 3 extra examples there. I might try and do the other examples from this, or the other questions from this exercise in other videos. We'll see how we go.